Okay, so our next speaker will be Jorge Sarmiento, and Jorge is actually going to channel Allison Gray, who's a postdoc in the SOCOM program, and speak about work on the actual CO2 Southern Ocean carbon uptake.
Okay, so, well, there's the outline and title. I put a question after it, but then my wife told me that's not a question, that's an assertion. This is Landschuster's version of the CO2 at the surface. This is degassing in the region where the ACC is, and you have upwelling. And then north of that, as Lynn pointed out, you have uptake occurring kind of at the very southernmost edge of the subtropical gyres. So have that structure in mind. What we're trying to understand is how these two, in terms of carbon for this program, what we're trying to do is understand, how these two processes balance each other out in the Southern Ocean. This was showed in a slightly different version by Nancy. It's all the data from the SOCAT, I think, version 2. And south of the equator here, the gaps in data are absolutely staggering. I keep looking at the Southern Ocean, but because of some of the results we just attained recently, I'm realizing that the subtropical gyre, I mean, what the heck is going on down here off of South America, is basically as poorly sampled as the Southern Ocean. And, but the color profiles here show the number of months that have been sampled. And in addition to the fact that sampling is rather poor over much of the Southern Hemisphere, less so in the Southern Ocean than in the subtropical gyres, interestingly enough. Almost all of these lines are in the color code indicating that you're only sampling 1 or 2 months out of the year. Basically, we're not getting anything in 10 months of the year in most of these locations. This is a map of all of the 50 floats that we have out there that I downloaded from our website just a few days ago. It's one of our graduate students at Princeton who got to go on a ship and look at all these, all these floats that are in this region making basically time series stations. We have 50 time series stations floating around in the Southern Ocean. I'm going to discuss results from only 14 of them that have been out there for 1 or 2 years, long enough that we can start to see the whole seasonal cycle for at least 1 year. Most of them are from a section in the Atlantic Ocean and another section in the Pacific. I'm going to discuss a lot of the results, or most of them, in terms of 4 zones defined by fronts in the Southern Ocean. The subtropical zone, which is the area where we have the blue or uptake occurring. And then this sort of transition zone, the subantarctic zone next. And then in the regions where we have the pink color indicating upwelling, we're calling that the Antarctic Circumpolar / upwelling zone. And then in this brown area here, this is the region that is covered seasonally by ice. Okay, this shows this next figure here shows the depth of the mixed layer in September, in the wintertime, and basically, whereas the upwelling is occurring in this inner ring, as you go farther away from the Antarctic, you get into these deep mixed layers. And it's interesting to see how the CO2 acts. Most of the CO2 uptake is occurring in the upwelling regions, not in the regions where the deep mixed layers are. Okay, I'm going to go through calculations that we've done with these floats using the methods that Nancy talked about to get at PCO2, and then I'm going to show you some delta PCO2 and CO2 fluxes. And there's this big surprise that we've discovered. Okay, here is shown the PCO2 estimated by the techniques Nancy went through. I've labeled all the Atlantic ones, and 1 Indian Ocean where we have, the rest of them are all Pacific. The bar coding back behind them, the bars behind them, the darkest bar is wintertime. And that's when you're going to tend to have the strongest winds blowing and so on. So we want to focus more or less on the wintertime to see what's happening in each of these regions. And so the top up here is the subtropical zone. And in the wintertime, you see that the PCO2 is below 400 parts per million. The PCO2 in the atmosphere at the time these things were out there was in the region between 390 and 400. So I put a line at 400. But basically, these data in the Pacific here, these floats in the Pacific, are lower than atmosphere, and so you'll be removing CO2 from the atmosphere. That's that blue area. This one odd float here out on the far right crosses a front, and so its behavior is, I'm gonna sort of leave it out of the discussion for now, because it's not behaving in this. When it crosses the front, it changes its behavior from the type of behavior that's characteristic of the subtropical zone. Then we have this transition region in effect, the subantarctic zone, where in the wintertime you're fairly close to the atmospheric value. This float 9095 is one of the ones, I guess just about the only float where we've had a real issue with a pH sensor having an uncharacteristically large drip. So I kind of graded out. And this far right Indian Ocean profile is sort of, or float is kind of complex. It's in an area where there's active eddies. And so these three floats I'll be saying less about than the ones that are sort of well within the zones here. Finally, we come to the Antarctic Circumpolar Zone, which is the one that's pink, red, where we have upwelling. And in all these regions, the CO2 measurements in the wintertime and the strongest winds and so on are higher than atmosphere, so in the direction of the red flux out of the ocean. These seasonal ice zones, first measurements ever under the ice during the wintertime when the ocean is covered with ice, shows that the concentrations are very, very high, but of course you won't get much gas exchange occurring during that period of time. And overall, the seasonal ice zone does not contribute greatly to the air CO2 flux. Okay. Now, I want to say a little bit. First of all, in the previous slide, I want to point something out to you that's very interesting. If you've read Taro's papers over time, the Takahashi papers in 2005 and 2009, you'll know about this. But there's something really interesting here. In the wintertime, in the subtropical zone, the ocean CO2 is low, and the summertime it's high. In the ACC zone, Antarctic Circumpolar, the seasonality is completely reversed. In the wintertime it's high. And Taro explained this as essentially being due to the phenomena I'll mention briefly with these next two slides. So this is the subtropical gyre when in the wintertime the CO2 is low. And what happens in the subtropical gyre region is the biology basically strips nutrients out of the surface fairly efficiently. And the surface CO2 is driven mainly by temperature changes, which is cooling in the winter. Cooling in the winter reduces the PCO2. And that's indicated by the fact that the float PCO2 shown in green is following more this red curve, which is the one that is due to temperature changes, than the green curve, which is the one that is due to everything else, which is mostly biology. In the wintertime, that means you're upwelling nutrients. In the summertime, it means you're stripping them out. But here, you're stripping the nutrients out most of the time, all year round, reasonably efficiently. And so you're pretty much following the red curve. Sometimes better than other times, or more clearly than in other times. Nevertheless, down here, all of the seasonal variability that does exist is due to the temperature. By contrast, in the ACC, Antarctic Circumpolar Current, the seasonality, which is high in the wintertime, is following the green line here, which is due mostly to biological processes, where you're upwelling extremely carbon-rich, nutrient-rich water to the upper ocean, that upwelling band, the pink band here, and that's causing the de-ice. You're stripping some of it out, but that's causing the blue line here to be high in the wintertime, and you're losing CO2 to the atmosphere. Okay. Now, let's take the PCO2 from that first slide in the ocean and subtract the PCO2 in the atmosphere, in this case from Cape Grim, nearby the Southern Ocean, and calculate the delta PCO2. And this is the first step towards calculating the flux. But another reason that I want to show delta PCO2 is that, and compare it with data, is that the delta PCO2 changes more slowly with time and as CO2 increases in the atmosphere than does the PCO2 itself. So the comparison of delta PCO2 estimated from the floats with measurements from the shipboard is easier to make. Okay, so I'm going to show you a close-up of the subtropical zone and the Antarctic circumpolar zone in the next two slides. And here, okay, in the subtropical zone, where PCO2 is low in the ocean because of following the solubility pump, the temperature, the PCO2 in general is negative, okay? So you're getting a flux uptake by the ocean. And shown on here are the estimates of Takahashi and Landschuster in the solid lines. The float is in the dashed black line, okay? And actually, in this zone, in the wintertime, the two estimates and our measurements are agreeing reasonably well in many of these floats. And we are also all agreeing pretty well with the actual SOCAT 3, version 3 measurements that are on the slide as well with these green points. In places where there are differences, which is more in the summertime than the wintertime, the float, it tends to be above. So it's taking up less CO2 than are the Takahashi Landschuster when integrated over the year, but by a smallish amount. Now we go to the Antarctic circumpolar zone. And this is really shocking. I mean, this is amazing. First of all, here, first of all, you can see that in the wintertime, in every single case, the float delta PCO2 is much, much higher than the mapped estimates or the SOCAT measurements. Well, there aren't any SOCAT measurements. That's the most critical point here. In the wintertime, essentially, the Takahashi Landschuster maps are pretty flat when delta PCO2, which I kind of read as essentially you have some data in the summertime, and you're just sort of mapping across from that across the wintertime. So, our estimates agree pretty well with theirs and with the shipboard where there are measurements from the shipboard, but everywhere else, especially in the wintertime, our PCO2s are much, much higher. Our delta PCO2s, which is going to give you a flux out of the ocean. Now you can go into detail, more detail in these other two zones here and here, okay? But these do not make major contributions, and for the sake of time, I'll skip going into detail on those. Now, take the ECMWF ERA interim winds, 6 hourly winds, multiply them by the delta PCO2s, interpolated. The measurements that we make are every 10 days or so. And so you get a lot of variability in here, which is due to the winds primarily. The delta PCO2 is somewhat smooth. And you see that on average here, in the subtropical zone, we're taking up CO2 and during the wintertime, and here, most of the year round. And in the ACC, we're degassing to the atmosphere pretty much year round, but especially in the wintertime. And now let's total these numbers up. These are all the individual profiles. This has parentheses because this is that float that had really big drift in the pH sensor. And we did not include it in these calculations. And this is the mean in each of these 4 zones, the mean fluxes. And the numbers in bold are here in the STZ and in the Antarctic circumpolar, subtropical, and some circumpolar regions. The bold means that these are statistically significant or statistically different from 0, which is not exactly the same thing. So that's why I've been emphasizing these two in my presentation. And now here, I show our float numbers from the previous slide in units of petagrams of carbon per year. So I've boldly gone where no man has gone before and used the mean from just those few profiles we have, or those few time series floats that we have, and estimated the flux for those regions, okay? So in the subtropical zone, we have a small uptake by the ocean in petagrams of carbon per year, but we have a very large loss in the Antarctic Circumpolar region. If we compare these with Takahashi and Landschuster, Takahashi and Landschuster agree pretty well with each other, both region by region and in the total. But our numbers, especially here in the Antarctic Circumpolar region, we have 1 gigaton or petagram of carbon per year difference in the direction of a loss of carbon from the ocean. When we sum up all the numbers, even in the subtropical zone and all the other zones, our models are all taking up slightly less than, rather our floats are on average taking up slightly less than the mapped values. And so the total difference that we get is a full 1.5 petagrams of carbon per year, less carbon being uptaken in the Southern Ocean than estimated based on the Takahashi Landschuster estimates, okay? So we're trying to, you know, we're in deep shock. I've been having great conversations with Peter Landschuster and various other people, Andy Jacobson and so on, trying to find a way, you know, maybe they'll tell me, well, you're wrong. I know you are, but they haven't done that yet. And some of the reasons that I've sort of convinced myself that maybe we're not wrong. You know, here's one. This is the Landschuster et al. Estimate I showed in the previous slide. Here is what we get if we subsample his map at the locations of our floats. And the number is a bit different, but it's not a lot different, okay? It would be hard to reconcile it from that by something like that. So I'm going to show you a little bit more about why. Well, okay. So I would conclude, based on this analysis, then, that the Southern Ocean CO2 flux to the atmosphere that we're getting is greater than previous estimates. Okay? 2 minutes. All right. So I have, you know, basically I'm trying to explore this 3 hypotheses. The first is that maybe there's flawed methodology. I hope that Nancy has convinced you that actually we think we can estimate the PCO2 from the pH pretty well. Of course, the small number of floats is worrisome, but the fact that all the disagreement that we get between our results and the previous work are in the wintertime, the main disagreement, when there are no measurements are available, convinces me, and that we agree with them when there are measurements available, suggests to me that we're on the right track. Obviously, we're going to continue to make measurements, but so let me go on. Here, we've drawn the air CO2 fluxes we get from Landschuster's time history, divided into our 4 regions. And so over this entire period, there is interannual variability, as Peter showed yesterday in his presentations, or this morning rather. Here's our floats, and it's this difference principally between the Antarctic Circumpolar Current and us that is what we're talking about. So is there some way that we could rearrange, that we could find something wrong here? And one of them is that maybe all of these are too low. They need to be shifted up, okay? And it seems to me that, well, our results in effect do support this, in that if they had measurements in the winter, Peter and company, the baseline should shift up. And that's something we can actually try. You know, we can give him our data and see if his neural mapping method will actually raise the baseline somewhat, okay? But, you know, if, nevertheless, So if there is a source in the Southern Ocean, as we suggested, and the baseline is now shifted up, that gets us in real trouble with the total carbon uptake, anthropogenic carbon uptake by the ocean, because we think it's 2.5 or so petagrams of carbon per year, and here we're taking away 1 of it. So where's that carbon going? I'm pretty convinced that the number 2.5 is right. And so that would suggest that there has to be a larger sink elsewhere to compensate for that Southern Ocean source. And my sort of candidate that I'm thinking about right now is that it's that subtropical blue zone that we just have barely sampled with floats so far. That may be the explanation. That's sort of the next thing I'm looking at. One other sort of final thing that could be wrong is that maybe that our values are anomalous. There's something funny that's happened in the last few years. And there are many, many indications that there is funny stuff going on in the atmosphere. Andy Jacobson could give a wonderful presentation, which he showed me on slides, about the El Nino stuff and its impact on the atmospheric CO2 and the hot waters in the North Pacific. The problem is, how do we get that to translate to anything happening in the Southern Ocean? But there is stuff going on in the Southern Ocean. This is a wind speed anomaly. The winds are much stronger right now. The water is colder right now in the last 2-3 years. And so maybe at least part of the explanation between that low baseline and our high numbers is that the baseline has moved up, as I've already suggested, and maybe the other numbers have moved down. And there is a fairly significant amount of space for some interannual variability in Landschutzer's analysis, maybe 0.5 petagram carbon per year. So that's my working hypothesis. And so future work, this is a quick summary. Keep adding floats, obviously. We've got 180 or 200 to go. Well, not 130 to 250 to go. The SASI analysis will be very helpful. And there are other constraints that we can test this against. We've already been discussing with Andy Jacobson, looking at the impact of these differences on atmospheric observations. Such a huge difference between what other people have been saying and us should easily be visible. Or if that's due to a time change, it should easily be visible at the time stations around the Antarctic. There are various other things we can do by looking at the ocean per se. I talked briefly already about trying the Landschutzer thing. And can I have 30 seconds? Okay. The last thing I want to mention briefly, because I think it's really exciting. Okay, so this is an analysis. There's so many things we can do with these data. I just showed this one thing because I'm just flabbergasted by it, and it's an amazing result. But we can do budgets of temperature, nitrate, carbon, with time along these float tracks. And there's one really interesting result. I'll just jump to the conclusion here, which is that the change in time of the carbon in the derivative of time of carbon inside the mixed layer is due to a balance between biological removal of carbon. Everybody here is familiar with that. But where does the carbon come from that is being removed biologically? Well, it's not coming from the air-sea interface. With temperature, with heat, it is coming from the air-sea interface, but the carbon that's being removed biologically is coming from transport and entrainment from below and lateral transport, et cetera. The gas exchange contribution, CO2 that's removed by biology, doesn't come from the atmosphere. It comes mainly from horizontal transport. The gas flux from the atmosphere is just a tiny part of the whole story. And I'll end there, sorry.
Thank you, Jorge. We'll save the... That's so provocative. If there's one question for Jorge, go ahead and give it to him while I change over, because it's provocative.